Well, good afternoon or good morning or good evening, wherever you are. I'm Doug Finke. I'm the managing editor of the Quantum Computing Report, and I want to thank Kevin for inviting me for this discussion. I think it'll be interesting and appreciate the invite. I'll start on, and I'll talk a little bit about my background. I think it's important for you to understand, where I'm coming from and what my background is, because that sometimes will flavor how I look at things. But I consider myself to be a refugee from the classical computing world. I spent many decades in classical computing. My first job actually was a mainframe design engineer at IBM in New York. And I worked with a lot of the major companies in classical computing. I worked for Intel for several years. Corning, working in optical networking, Western Digital on disk drives, did a whole bunch of startups in a variety of different areas. Went through the PC era where I saw a lot of PC companies come and go. And in 2015, I sort of got tired of doing it. I'd been doing it for a long time. And I started getting interested in quantum computing because a lot of my previous positions dealt with high performance computing. And I started to see that quantum computing was a new paradigm for achieving higher performance that was completely different than anything else seen before. So, I started going through the web and looking at what was there. And, there was no one who was reporting on what was happening from a market analysis standpoint. And I was used to that in classical computing because in classical computing, you see a lot of these analysts who will tell you what IBM's done next, what Intel's next microprocessor is going to be, and those types of things. The only things available at 2015 were really these very, very technical PhD level talks that was really meant for other PhDs. And occasionally you'd see these gee whiz type of things in popular science where they would say, Mr. Spock would teleport his quantum qubits or something like that. But no one was really providing something at that, what I would call that intermediate level, that could explain to people who were maybe who understood technology a little bit, but was not as deep as the PhDs, but without the hype and without the things that you might see in the popular science. So in late 2015, I started Quantum Computing Report. At that time, the only commercial company out there was D-Wave. They had, I believe it was 128 qubit quantum annealer. And I started tracking it as more as a hobby than anything else. And just a few months after I started, IBM came out with the IBM Quantum Experience. It was a 5 qubit machine that you could access over the web for free. And I actually did the first review of that machine. I still remember it's called Inside Looks at the IBM Quantum Experience. And from then on, the Quantum Computing Report has really grown as the industry has grown. So a little bit about the Quantum Computing Report. It is primarily a website that has a number of different areas in it. And it's really meant, as I was just saying earlier, as a service to the industry. We have a news section that reports on news. And then we have actually 2 different analysis sections. We have analysis with the A, really focuses on business side things, trends we might see in the industry and that type of thing. And then Q analysis will focus more on more technical items, things that we see happening in the industry. We do have, I believe, the most complete listing of what I call players in the industry. Any company that's involved with quantum computing or quantum communication, I will list, and it's actually separated out into private companies, public companies, universities, governments and nonprofits, those types of things. We also have a very good listing of resources. You want to know where all the conferences are and links to all the conferences, we have them there. We have various tools. A page lists all the various tools. There's a lot of industry associations. We will list those types of things. And then we do have a premium section. Some of the databases in this are premium, which means it's behind a paywall. There's $100 a year membership for that, but that helps pay to sustain the website. And the scorecards is one of those areas behind the paywall. But there we have a listing of all the what I call qubit counts, who has how many qubits. We have a listing of qubit quality, where we report things like gate fidelities and coherence times and gate delays, things like that, as well as a qubit technology map that shows all the companies developing hardware for quantum computing and what technologies they're using, from superconducting, ion trap, photonic, and NV diamond, etc. And then we have a jobs page, a popular page for jobs, which we list all the jobs that we see publicly posted in both worldwide. There's one page for the US, and then there's one page for, actually one page for US and Canada, and another page for Europe, Australia, and Asia. And then if you want access to the premium pages, you can do that through the membership. So over the past 7 years, we've collected over 800 pages of material, and even they're all still on the website. We don't delete anything. Even some of our earliest articles are on the website. So it's a great resource. And one of the things is very, very helpful is there's a search bar here. So if you ever wanted to find out all the news articles of, let's say, Rigetti or IonQ or something like that, you can type it in the search bar and it will pop up all the articles we've written over the past 7 years about those companies. And then finally, we do issue a newsletter every Sunday that's free. So I would recommend everyone sign up for it. That will basically summarize the events of the past week. And it's a great way to catch up on what's happening. I know many of you are probably very, very busy. It's hard for you to keep up with all the news releases throughout the week, but we purposely issue on Sunday because people have a little bit more time. They can take half an hour or so and just browse through and sort of catch up on what happened in the previous week. So let me talk a little bit more about the challenges and sort of what I think will be happening in the quantum industry. And if there's one thing I'd like you to take away from this presentation, it's this slide. And it's something called Amaras Law. And sometimes you'll hear Bill Gates quoting it. And what they say is people tend to overestimate the effect of a technology in the short run, but overestimate in the short run, but they underestimate what happens in the long run. And I think we see that today in quantum. There is a lot of hype in quantum. I think people are overestimating how quickly and how soon we'll really be able to utilize quantum for quantum advantage. And it's going to take many, many years. I'll go into some of the challenges in just a second. But I also think that over the long term, and long term is really more like 15, 20, 30 years from now, there will be applications that we haven't even thought of. And it will have a big impact, but people just need to be patient because it's going to take a long while. It's a tough technology. So people will have to have to wait and be patient before it happens.
And then, so Doug, I know that slide was important to you, but I don't think we're quite seeing it on our end. It says 1, and then that main slide is 1. Like Marlo said, maybe the F5 button or.
Are you seeing any of the slides I'm presenting?
Yeah, we just see the first one. It's just stuck on the first one.
Oh, it's stuck on the first one.
Yeah.
Oh.
I did because you said it was important. Okay, now it's advancing. The QCR now has, okay, then a curve.
You see it now?
Yeah, it's the one that says 800 pages of material in the text.
Okay. You see it now?
Yeah, Amaras Law.
Okay, hold on for a second. Hold on, I'm doing.
So you got a couple more people coming here. So Ravi, we'll have to get him on
I
sometime.
can't hear you. Hold on, Kevin. I have an issue here.
Okay, so Robbie's coming. Hopefully, everybody else can hear me. So Robbie's been coming for a while. He's coming from the other one, I think, as well. But yeah, just if you guys have questions for Doug, eventually, we can see Amaras Law, Doug. So
Okay. Okay, there you go. You still see it, right?
yeah, there you go. So
Okay,
it's
I
full
got it
screen
fixed.
Amaras Law.
Yeah. Okay. So this is Amaras Law again. People tend to overestimate the impact of a technology over the short term, but they underestimate it over the long term. And this is a very, very important concept because we see that over and over again in technology. So if you want to think about how the quantum computing industry will develop, I think sometimes it's useful to see how other industries have developed in the past. And the examples I would use is the semiconductor industry and the personal computer industry. In both of those cases, there was a large number of startups, a lot of excitement, and over the years, it's winnowed down to a handful of players. There's been a lot of big successes in the PC area, for example. Dell Computer and Lenovo have been successful, but there have been a large number of companies that have dropped out, and you can see here at the bottom all the list of companies that are now that were popular in personal computers that are now defunct. So I expect that to happen, or I expect something similar to happen in quantum computing. It is going to be a very, very, very dynamic industry, and there's going to be a lot of changes over the next several years. We still have a lot of startups coming in. I typically add by listing 1 or 2 startups every week, but almost none of them are profitable. They're all trying to get venture capital funding, but none of them are sustaining their own operations, or very few of them are sustaining operations. And you can see that there are, of course, IonQ and Rigetti are now public companies, so you can see the reports. They are losing money, but of course their projections are that, let's say 4 or 5 years from now, they'll make money. We do have over 250 startup companies that are working in quantum listed on our thing. But I think what you'll see is a lot of that list will consolidate. You will see a lot of mergers, and we've already seen some over the past 12 months. Of course, the big one was Continuum and Cambridge Quantum. We just saw one a couple weeks ago between Quantum Machines and QDevil, and there was and there'll be some more. So in some cases, people will just consolidate, and sometimes to get access to the engineers. Sometimes you'll see hardware and software companies combining in order to provide a more complete solution. And the listing of companies, my prediction is that the listing of companies that I will have on my website, let's say 3 years from now, will be much, much different than what I have today. Now, the other thing that we will see is a lot of competition also. Competition hasn't been really very fierce right now. People are still more in the technology development era, but as it gets more real and as people start looking for more and more paying customers, it will get fierce. And there's a lot of different levels of competition that we'll see. There are a lot of software companies out right now, and I think they will compete with each other for the various platforms and solutions. The good news is that many of them have different approaches. Some of those approaches may not work out. Some may work well. Similar on the hardware side, as we have about 10 different technologies that are all competing right now: superconducting, ion trap, photonic, cold atom. All those are competing, and some of those will drop out just because people can't get to the level that they need to be competitive. I don't think all of them will drop out. People ask me, do I think it will be a winner take all market? And I don't think so. I think, again, 10 years from now, there'll maybe be 3 or 4 technologies that are still out there. And part of the reason for that is some of the technologies will be better for certain applications than others. But you probably won't have 10 really competitive technologies anymore. The other thing that people should not ignore is that the classical guys are not going to give up. That classical computing is continuing to improve. That people, sometimes I see in presentations, well, Moore's law is slowing down, and we're going to have to move to quantum because classical won't be able to improve anymore. That's really not the case. There is still a lot of innovation left in classical computing. Much of it is in new algorithms. Much of it is in what I would call non-von Neumann architectures. And people are still very, very innovative, and we will still see many, many solutions that will compete with quantum. You hear the term quantum inspired. A good example would be something like the Fujitsu digital annealer, which competes against D-Wave and their quantum annealer. So the thing to remember is, if you're an end user, you're not going to care what solves your problem as long as your problem gets solved. You don't get any extra point. I don't think, for most people, you won't get any extra points for having a quantum solution when a classical solution will suffice. The other thing that I think you're going to see very heavy activity very, very soon is in this notion of quantum resistant cryptography. I think everyone here has heard of Shor's algorithm and how that future quantum computers will be able to break the public key cryptography, the asymmetric encryption that we use today in today's internet. And what is that? That's going to require is upgrades or replacement over the next 20 years of billions of devices, tens of billions of devices, and the cost will be billions of dollars. It's going to be a wholesale, complete change in the way we communicate, our digital communication infrastructure. And there are going to be a lot of solutions out there. And in fact, some of you may remember the Y2K 20 years ago. We're going to see similar type of effort over the next 10 years. And there are 2 solutions. There are 2 basic forms of solution. One is the quantum key distribution, or QKD, which is the physics-based approach. And the other is PQC, which is the post-quantum cryptography approach. Now, on the latter, the US government agency NIST, the National Institute of Standards and Technologies, has been working on coming up with new software-based algorithms that would replace things like RSA, but cannot be broken by quantum computing. They started about 5 years ago with 69 algorithms. And the thing to watch out for is, within the next few days, they're going to announce their first set of algorithms that they will standardize. And that is going to be a big announcement. And again, it's going to happen this month, right? I believe it's going to happen this month. And that's going to start a big wave of companies starting to implement quantum resistant technology in their systems. And it's a big effort. As I said, it's going to be billions of dollars. And but enterprises will be very, very keen to do that. It's going to take about 10 years to make that transition. But people will want to start now. They've just been holding off just because they're waiting for that final go-ahead from NIST with the selected algorithms I think the last round they had something like 12, and they'll maybe announce 3 to 5, something like that, again, with the next few days. But one thing that most people don't realize that I'd like to point out is that, from the standpoint of a CIO, and they start looking at their budgets, my prediction is that this decade, let's say from 2022 to 2030, enterprises will actually spend more money on making their systems quantum resistant than they'll actually develop on developing new applications. And there'll still be a large amount developing, new applications. We hear from all the consultants that you got to start now, you got to do stuff. But the way I see it is, if you're a CIO, you're going to place your priorities first on the defensive side, make sure that you're not hacked. And that's going to get a little bit higher priority than what I call the offensive side of creating a new application. So just to talk about some of the challenges that the industry is going to have, just to wrap up, hardware still needs to improve. Right now we're at 127 qubits with IBM, but the systems are going to have to scale to millions of qubits in order to do some of the applications that we see. Companies like Microsoft, Goldman Sachs, and others have actually done some pretty deep analyses of how many qubits they need and what quality level of qubits they need to implement specific algorithms. And the numbers are at least very high, at least compared to what we have today. But the challenge for the hardware guys is not only to scale the number of qubits, but also scale the quality of the qubits too. Because if you talk to the programmer right now, or someone who's actually programming this stuff, that the error rates of even today's quantum computers are not good enough really for them to do any useful work. Another thing that I think is going to be a big thing that the hardware guys are going to have to put together is that many of these large systems will be put together as a network of smaller quantum processors. This is the approach, for example, that PsiQuantum is taking. IBM will be taking it. Google will be taking it. It's been on the roadmap. IonQ is taking that. So they will have to figure out how to connect multiple processor chips together, and that's non-trivial. I think the first company that's done a little bit is Rigetti, who just taken two 40-qubit chips and now has an 80-qubit with the two combined. The software companies have lots of development left. Big problem is that the software is not easy to use yet. They have to make it easier, and it has to be programmed at a higher level. There are a handful of companies doing that. I did write an article called Quantum Programming for People Who Don't Want to Learn Quantum. And companies such as Multiverse Computing in Spain has developed an application that you can just fill out a spreadsheet and will automatically try to figure out how to solve that. A company in Singapore called Horizon Quantum Computing is working on a software that will automatically convert a classical MATLAB program or a C program to run on quantum. We're going to need more libraries, and then we're going to need more lower level software like compilers and pulse control programming to get higher efficiencies and fewer errors. Companies that do that, for example, would be Q Control in Australia. And then the software companies are also going to have to figure out how to take advantage of a networked quantum data center, like I was just saying above for the hardware guys. This actually was a big, big thing for classical computers. Is roughly in about the 1980s. That's when the classical computer systems, maybe the 1990s, started going to the network approach. And you have to rethink how you do your software. It's not trivial. So software guys are going to have to do that. And then you have some non-technical things that are really critical for the industry. Workforce. We're going to need thousands of future workers who understand quantum and know how to program them. That's actually a topic of almost every conference that I go to. There are becoming more and more efforts to create standards. to create common terminology, standards, benchmark programs, intermediate representations of programs, so machines can be more interoperable. And this is going to be a big effort, sort of like creating the way Fortran, when it was standardized in, like, I think the 1960s, that helped people move from one machine to the other. Before that, you were pretty much stuck with a machine, whoever you had that you wrote your software for. So, and as an example, there's like 5 or 6 different benchmarking protocols or benchmarking proposals out there right now. And another issue that I think we're going to see more and more of is just, I call it international cooperation. There are a lot of countries that are very concerned about export control, immigration restrictions. And one thing that I think all governments going to have to do, including the US government, is to figure out how to create a model that minimizes those issues but still protects national security. So that's my introduction. Again, here's the website. If you want to learn more, my email is underneath that. I'd be happy to answer any questions, and we'll see what you have. So Kevin, I'll take it to you, see if you have any questions coming up.
Yeah, this is awesome. And for me, it's like a kid in the candy shop, just because, like, I'm always looking at the most recent news for these discussions. I think, Russ, at one time you said you subscribed to this.
Yeah, I'm a
Premium.
$100, Doug. It's well worth it, and I recommend it to anybody else. Especially, I find the scorecards are just fantastic. I don't see that data anywhere, and it really helped me in my early learnings about trying to compare different systems and sort of think about how people measure these things, because everybody's always bragging about their performance or their numbers of qubits, but it's a little more nuanced than that. And I think that scorecard is a fantastic resource.
Yeah, so there's a recommendation there, Doug, for the
okay. Well, thanks, Russ.
And the listing of the venture investors also I've found really valuable. So those 2 things make it very worth it to pay the premium. Happy to do it.
So I could talk to you for hours about this stuff, just because with D-Wave and all the partnerships, I wrote a report myself on partnerships in 2021, and I called it basically the year of partnerships, and they continued this year. And like you highlighted, the big one with Quantinium. So obviously with standards, so Marlu, she works at NIST. I know there's NISC, NISQ. And actually next week, David Shaw of it's Real Fact-Based Insight, something like that. He wrote this huge report too, that basically said a similar thing as you, as like IBM is leading as far as superconducting qubits with fidelity, 99.9 something percent, but it all needs to get better. So I guess, where do you see some of this stuff going with quantum, with the standards? Do you have could you talk a little bit more about that?
Yeah, it's going to take a while. And perhaps part of the issues, there are multiple groups looking at this. The IEEE is looking at this. They have a quantum standards and terminology group. Another group that's looking at this is the Quantum Economic Development Consortium.